Okay, so other ways of visualizing velocity fields include streak lines and path lines. And these can be a little weird to conceptualize until we realize that they're kind of the same thing as long as the flow is steady. So a streak line is a line that touches all the particles in a flow which have previously passed through a point. So in the example that we've been following, here's a particle. And that particle at one instant in time has a velocity that looks like this. But we know that the velocity field follows something like this, and so this particle, as it moves through time, is going to follow this here. And strangely enough, that's the streamline we just drew. It's the same thing as a streamline. When steady. I'll show you an example in just a minute that clarifies what I mean here when it's not steady. A path line, once again, is also the same as a streamline when steady. But when they're unsteady, they're different. The path line is the path of a single particle, and so you could think of this almost like tossing baseballs. Right? We throw a baseball, it follows a path. The line that that particle follows is that particle's path line. So here's how it's going to be defined, just like you'd do the flying baseball. So if we have some position x of time and y of time of a given particle, you know its velocity looks like dx dt, and its velocity in the y direction looks like dy dt. And so again, we separate and integrate here just differently. This time we're going to multiply up by dt. And so we get something that looks like u dt has to be equal to v dt. Oops, that's an error. Go ahead and erase that completely from your memory. What I meant to say was that u dt is equal to dx, and v dt is equal to dy. And so if we have functions for u and v, we could integrate these with respect to time. Remember last time we were integrating with respect to space, and we end up with something that gives us a function x of time equals something, y is equal to something else, and this is the equation of the lines of motion of a single particle. Okay, so there's this example in chapter 4 that really drives this home. Let me just sketch it out for you. Imagine we have a sprinkler head. So this is my terrible artwork of a sprinkler head, and if it's stationary and I turn it on, it shoots water through a series of nozzles like this. That's all it does. It just shoots up. And so you could imagine that this follows a path. If you followed a single drop of water, it would follow a path that looks like that. And lo and behold, this would simultaneously serve us as the streamline, the streak line, and the path line. If I follow a single particle, it's going to go up and over this streamline, and all the particles that pass through this point are also going to have done that. And so we just get this one line. But if I were to let this thing start moving, right, we've got these oscillating sprinkler heads. So now all of a sudden it's moving sideways like so. There is, at an instant in time, the velocity of the particle that is being shot out, but added to that is the horizontal motion of this business. And so the actual velocity vector at one instant in time looks like this, v of t. And this one particle, once it leaves, we're never touching it again, it's going off like so. And so this would be the path line of that particular particle. If this is oscillating, at some point it's moving back, and so another particle is going to experience the situation where it sees the exact opposite of that. And so at some other instant in time, the velocity might look like this. And the path line of this particle is going to go out in this direction. And I suppose that, we know eventually these things are going to arc down on us like so, but that's a different issue. This is the path of a single particle. The next particle that leaves this location, because it's moved, has a different one. And so this could be at one instant in time, this particle has this path line. At another instant in time, moving through the same point, the path line looks like this.